Hey, it's Mr. Lowry. This is going to be some of what we covered in class today on 11:30 if you're in A cohort, or 12:1 if you are in B cohort. This is kind of some of the notes and ideas we discussed for day one. We already, in the notes before this video, I talked a little bit about converse and contrapositive, inverse, and conditional statements. So if you haven't read that, I would go back and look at that first, because you're going to need to know that. Page 77 is a really good resource for talking about conditional statements and finding their converse, inverse, and contrapositive. In this video, we're going to set up a proof, and then we're going to solve a proof. But in order to get there, we got to talk a little bit about a few theorems that we've proven, a few postulates, and what a converse is. Or a converse of a theorem that we have. So right now I'm on page 134 of your textbook, and you all should have textbooks now. There's three theorems here that we discussed last week: the alternate interior angles theorem, the consecutive interior angles theorem, and the alternate exterior angles theorem. Okay, so we proved a couple of these. The consecutive interior angles theorem, remember, is very similar to Euclid's fifth postulate. So if you want to use this language, that's fine if you're doing a proof or something. But when we talk about it, we say Euclid's fifth because we like to kind of go from the Euclid's postulates. Okay. On the previous page, this is page 133, we have what's called the corresponding angles postulate. Okay. Now your book takes this as a postulate. We actually proved this in class last week, and so we called this the corresponding angles theorem. You can call it either, it's up to you. But one of the things I wanted to highlight is how your book uses different postulates. Right? So we use Euclid's fifth postulate, Euclid's five postulates, as kind of our basis. I like to always connect geometry back to the ancient Greeks because they're kind of what are the famous for doing that kind of math. And there's a little bit of a controversy about parallel lines and what you can assume when you have parallel lines cut by a transversal. The book assumes some things, and it's slightly different than what Euclid assumed, but you kind of get to an equivalent area, and we're going to talk a little bit about that. So again, we proved this as a theorem last week in class. But those are important ideas. Basically what they talk about is parallel lines, like this. Let me zoom in a little bit. You might need to look in your book so that you can kind of see this a little bit better, because my camera is only so good. But the idea behind these theorems that we talked about are parallel lines cut with a transversal. When you have parallel lines cut with a transversal, you get a bunch of other stuff for free, a bunch of other information. You can conclude, if these two lines are parallel, that the alternate interior angles are congruent, like 4 is congruent to 5 and 3 is congruent to 6. You can assume that the opposite exterior angles are congruent, so 1 congruent to 8 or 2 congruent to 7. You can conclude that the corresponding angles are congruent, so 1 is congruent to 5, 4 is congruent to 8, 3 is congruent to 7, 2 is congruent to 6. And you can conclude that the consecutive interior angles are supplementary. So measure of angle 4 plus measure of angle 6 equals 180. Measure of angle 3 plus measure of angle 5 equals 180. And those are all either theorems or postulates that we talked about or proved last week. What we want to talk about today is the converse of some of those ideas. We're going to specifically focus on this guy, the alternate interior angles theorem, which says if two parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. We're going to talk about the converse of that, and we're going to prove the converse of that in just a minute. Okay? So from there, once you kind of have reviewed a little bit about those theorems that we talked about and you're comfortable with those ideas, we're going to jump over to section 3.5, which also talks about some similar ideas. Okay? I wanted to point out a few things to you. Again, this kind of comes down to postulates and what the book assumes and what we're going to assume. Okay? So here is another postulate that the book gives as just something that you don't have to prove, right? Postulates you don't have to prove. And it's about corresponding angles. Okay? This postulate kind of is the converse of what we talked about. It's the converse of the corresponding angles postulate. So instead of starting with parallel lines and concluding that the corresponding angles are congruent, this starts with corresponding angles congruent and assumes that the line, and then concludes that the lines are parallel. So this right here, 3.4, is really, really similar to an idea that we saw earlier in the book. So this is on page 151. Okay, compare that to postulate 3.1 on page 133 that we just talked about. Okay, this is the corresponding angles postulate. Okay, this postulate right here is the converse of that statement. It's the flip of it. Okay, this assumes corresponding angles are congruent and then concludes that lines are parallel. This guy assumes that the lines are parallel and concludes that the corresponding angles are congruent. So it's the converse, right? But in your book, these are both postulates. Okay, if you look a little bit lower, you'll see this construction here. And this basically is just a construction on how to make parallel lines. If you only had a compass, which is like this little tool that makes circles, and a straight edge, you could make parallel lines by taking this angle and copying it. So what's happening in here is they're taking this angle right here, and they're making a point, and they're copying that angle a little bit higher. So they've taken this angle, and they've copied it up here. So now these two angles are congruent, they're the same, because they copied it. And then they're showing that, hey, those lines are parallel. Okay. When you start with geometry, you always have to start with postulates, right? In this book and in a lot of geometry, they start with ideas about corresponding angles, okay, and parallel lines. That's where they're going from. And they build kind of from there. If you flip over the page, you'll see that there's this thing called the parallel postulate, and this says here that Scottish physicist John Playfair provided the modern version of Euclid's parallel postulate, which would be Euclid's fifth postulate, which states there's exactly one line parallel through a given point, not on a line. So this parallel postulate, 3.5, along with postulate 3.1 and along with postulate 3.4 that we just kind of talked about, are essentially a replacement for Euclid's fifth postulate. It's a very, very similar assumption, but it's slightly different in that these have to do with corresponding angles and not consecutive interior angles. Okay, so let me explain that really, really quickly, and then we'll finally get into the proof. And there's a lot of setup for this. Sorry, this is the idea about Euclid's fifth postulate has been debated on whether it's obvious enough or not. So let's kind of talk through that debate a little bit. Okay, this is what Euclid said. Euclid has these lines, right? And he has this transversal. And Euclid says it should be obvious to anybody who's, you know, a geometry person that 1 plus 2 has to equal 180 if these are parallel. Or if these are parallel, these have to add up to 180, right? Or if these don't add up to 180, these will have to cross at some point, or something like that, right? That's the whole idea behind Euclid's fifth postulate. It has everything to do with consecutive interior angles. He made a lot of assumptions about consecutive interior angles and the idea that they add up to 180. That was his assumption, and he kind of shows like, hey, this should be obvious to anybody that's kind of, you know, a geometry student. Now, a lot of people decided that's not obvious enough. You actually should probably prove that or something like that. And there's been this debate about Euclid's fifth postulate and whether it's valid. So a lot of textbooks or a lot of geometry, they don't start there. What they do is they start with parallel lines, with a transversal, and they start with corresponding angles instead of these two. They say, okay, look, it should be obvious that this one and this two are congruent. Instead of saying these have to add up to 180, it's a little bit maybe more easy to see these got to be the same thing, and vice versa, right? If these two lines are parallel, then these have to be congruent. Or if these two angles are congruent, then these two lines have to be parallel. So they assume something about corresponding angles and its converse in order to build the rest of the geometry stuff. Okay, so when we're proving stuff about parallel lines, we kind of have to decide which postulates are we going to use. Are we going to use the ones provided in the book that are about corresponding angles and parallel lines? Or are we going to go back to the old school, like literally the old school, the school of Athens, basically, and talk about, assume things about consecutive interior angles? Okay, and these would be corresponding. It all depends on what you feel like is the most obvious thing to assume. We have to assume one or the other, otherwise we can't get any further. And again, there's a little bit of debate on which is the best way to go. Okay, I always like to connect math back to the ancient Greeks, especially geometry, because I think it kind of makes it more human. So as we've talked about these different proofs that we've been doing, we've been using Euclid's fifth postulate quite a bit. And I think that's what we're going to do for this next proof. All right, so finally down to business. Now that we've kind of laid that foundation and established that, that debate basically and talked about what we're going to use, okay? What we want to talk about is the alternate interior angles theorem, alternate interior angles theorem and its converse, okay? And what we can assume and what we shouldn't assume. Okay, this is kind of it in a nutshell. This is some abbreviation here. Alt-int angles theorem, right? If L and M are parallel, if two parallel lines are cut by a transversal, so we're going to assume L and M are parallel, then angle 1 is congruent to angle 2. These alternate interior angles are congruent. Okay, that's the alternate interior angles theorem. We actually proved that last week using Euclid's fifth postulate and some linear pairs, the supplement theorem. Okay, what we're going to try to prove now is the converse of that statement using similar ideas. So we're going to switch this statement and this statement. We're going to flip them this way. We're going to make the then the if part, and we're going to make the if the then part, and that's the converse. So if angle 1 is congruent to angle 2, then L is parallel to M. Okay? We're going to try to show these are parallel. Now, the things that we want to use here, or the things that we can use, or we can use Euclid's fifth postulate, because that's kind of one of our foundation things. We can use vertical angles. We can use supplement theorem, basically things that we've already proven. Okay, so let's see if we can write this out and go from there. Okay, so we got our figure here. We're going to label it kind of similar, but I'm going to add a helper angle. So I'm going to add 1, 2, and then 3 here. Here's L, here's M. Okay, now we don't know these are parallel yet. Okay, this is the converse. We're not assuming they're parallel. We're assuming 1 and 2 are congruent. What we want to prove is that these are parallel. And that's kind of hard, especially after you already know this one, because if you're like, oh, well, it should work both ways. But again, logically, the converse of a true statement isn't always true. That's why we have to prove it. Okay. So here's what we got. We got given angle 1 congruent to angle 2, right? We're going to use the if part. We want to prove L is parallel to M. Okay, let's do our table here, or our two columns. We got statements, we got reasons. Okay, and we're going to start by saying angle 1 is congruent to angle 2, given. Okay, I'm going to put a couple steps in here. I've actually done this before today, so I know how many steps it's going to take. You probably wouldn't know that just starting off, but this is how many steps it's going to be. All right, now let's talk a little bit about Euclid's fifth and what we can conclude. Okay, Euclid's fifth, again, we have to assume it's true as a postulate. And we kind of also assume that its converse is true at the same time as a postulate as well. And so what we can say is if 2 plus 3 equals 180, then these are parallel. Okay, so another way of stating Euclid's fifth in this situation is if measure of angle 2 plus measure of angle 3 equals 180, then L is parallel to M. Okay, remember Euclid's fifth postulate's nickname is the parallel postulate, right? And it's about parallel lines. Okay, so this idea right here, we can say if we want to say this, we could use the justification of Euclid's fifth postulate. Okay, so if we can show 2 plus 3 equals 180, then we're pretty much home free. So our second to last statement is going to be measure of angle 2 plus measure of angle 3 equals 180. Okay, our justification for that, we don't know yet, but if we get that far, then we can say L is parallel to M by Euclid's fifth postulate. Okay? All right, so basically what we need to do is find step 2 and step 3 and then justifications for 2 through 4. All right, let's go back and actually from here, what you should probably do is pause the video and see if you can finish this up. Because with the information that you have and the experience you have, you should be able to finish this already. Now, of course, proofs are a little bit tricky, so you might get stuck. But pause the video now, see how far you can get on this. Okay, coming back from pause. Hopefully you got some ideas here. What I would probably do next in step 2 would follow directly from step 1. I need to talk about what this idea means. What does congruence even mean? Well, it means the measure of angle 1 is equal to the measure of angle 2, right? They have the same measurement. And the reason for that is the definition of congruent angles, okay? My abbreviation for that is def of cong. It's what congruence means. Def of cong is definition of congruent angles. Okay, cool. So let's go from there. If we look back at our figure, which is important here, we're talking about these two angles, right? These two alternate interior angles. Again, we're assuming the alternate interior angles are congruent and showing that L has to be parallel to M. The other angle pair that we have is 2 and 3, which we know are consecutive interior. We're trying to show those equal to 180 in step 4. And the only other pairing is 1 and 3. So let's talk about 1 and 3. What is the relationship between 1 and 3? If you said linear pair, you are correct. So what we know is the measure of angle 1 plus the measure of angle 3 equals 180, right? These two have to add up to 180. Why? Because they're a linear pair, and that's the supplement theorem. So I'm going to put supplement theorem as my justification there. Okay, so angle 1 plus angle 3 equals 180. And we want to show that the measure of angle 2 plus the measure of angle 3 equals 180. But we know that measure of angle 1 and 2 are equal. So if I take this statement and I replace this angle with angle 2, I got what I'm looking for. So all I got to do is replace this guy with measure of angle 2 because they're equal. So think about what property of equality allows you to replace something with what it's equal to. That's the substitution prop of equality. So subst prop of equal. And that's pretty much going to get us there. Okay, so we start with the congruent, the alternate interior angles are congruent. That's given. That's what we're assuming. We show that they're equal in measure. We use 1 and 3, that linear pair, and we use the supplement theorem. We do a substitution to get 2 plus 3 equal to 180. And then we're like, hold on a sec. If 2 and 3 add up to 180, then these are parallel by Euclid's fifth postulate. And so we basically have proved that L is parallel to M. So what have we shown? By this figure, we've shown that if we have lines that are cut by a transversal and the alternate interior angles are congruent, then the lines have to be parallel. Okay? So once again, last week we proved if the lines are parallel, the alternate interior angles are congruent. Here we proved that if the alternate interior angles are congruent, then the lines are parallel. That's the converse of this statement. This is the converse of the alternate interior angles theorem. Okay? So, along with that, you got some other ideas here that are converses of things that we've already talked about. Okay? Let's look at 3.7, for example. This is back on page 152. This says, if two lines in a plane are cut by a transversal, so the alternate interior angles are congruent, then the lines are parallel. Okay, this is the converse of the alternate interior angles theorem. We already proved that if the lines are parallel, alternate exterior, did I say exterior? Sorry, we just talked about that. I wanted to look at 3.5. This is the one we just proved. This one says, if two lines in a plane are cut by a transversal, so alternate exterior angles are congruent, then the two lines are parallel. So last week, another thing we proved is if the lines are parallel, alternate exteriors are congruent. This theorem says that if the alternate exteriors are congruent, then the lines are parallel. Right? It's the converse of something that we previously proved. All right, so these are things that you're going to need to know, facts that you're going to need to know. If you want to add them to your notes, that's fine. You don't necessarily have to, as long as you kind of understand what they mean. So all the things that we talked about with angles and parallel lines, the converse is true. So let's talk about that really quick. If the consecutive angles are congruent, the lines are parallel. If the alternate interior angles are congruent, the lines are parallel. If the alternate exterior angles are congruent, the lines are parallel. If the consecutive interior are supplementary, then the lines are parallel. Okay? The converse of those 4 facts that we talked about in class last week. If you pull up your notes and you look at those, you can just write converse also true. Let's just flip back really quick, back to 3.2 where we talked about those ideas. Okay? So, postulate 3.1, its converse is also true. We talked about that already. These 3 ideas, also from last week, their converse is also true. And those are all the things in section 3.5 that we were looking at. They're converse statements of these 3 statements. So compare page 134 with that page we were just on, 152, and you'll notice that we have basically converses. Okay? We're not going to prove them all, but I wanted to give you an example of one proof of a converse and how we can get there using Euclid's fifth and some other things. You could prove the other ones true in a similar manner. The proofs are similar, but we don't have time to go through them all. I hope that helped. I know that's a little bit tricky, especially with like what can you assume is true and what can you not. And again, the book assumes a few different things than Euclid, slightly different, but they get you the same results. So thanks for watching. Appreciate it. Tune back in a couple days. Log back into Canvas and see what your assignments are. There was no new assignment for tonight's homework, but you definitely want to be aware of those theorems and postulates we talked about because we're going to be using them this week. Thanks.